Before we start going over some practice problems for type 2 projectiles, I want to give you some background information. First of all, some important terms that I'm going to use are resultant vector, and that refers to the hypotenuse of x and y component vectors. And I may also use the term rationalize, which means to break a vector, break a resultant vector, into its x and y component vectors. Most of your easier type 2 projectile problems will give you a starting hypotenuse, an initial velocity launched at some angle. And then you are going to need to break that vector into x and y components using sine and cosine. So that's the example that I've got going on here, and that's how the example problem is going to work that we're going to go through today. So first of all, we've got v naught here, and so what I'm calling v naught is this vector right here, mainly because it's helpful to give it a very different name from vx or viy. So v naught, that refers to the initial velocity, whatever the starting velocity is, that's launched at an angle. So when I give you v naught, or when a problem gives you v naught, it's going to say something like the projectile was launched at 14 meters per second at 32 degrees above the horizon. So usually that's with respect to whatever the horizontal axis is, whatever this x-axis is, usually with respect to 0 degrees. So that is what this is supposed to be looking like. If this was an xy coordinate plane, this down here would be considered 0 degrees. Up here would be considered 90 degrees. Over here, this direction would be considered 180 degrees, 270 down at the bottom, 360 over where 0 is again. So that's the idea, that we're saying everything relative, we're identifying things relative to that positive x-axis where 0 degrees or 360 degrees would be located. So now the other important things that we need to know about are how are we going to get this vector rationalized in the first place, break it up into the y and the x. Well, we practiced last week in class, that if I have a vector like this, I have the hypotenuse and then I have an angle, that I am going to be using one of my trig functions to find out what this length is, this vertical length right here. So am I going to use sine, cosine, or tangent to solve for this one? Well, since this is opposite and I have the hypotenuse, I'm going to be using sine. So that means that we're going to take v naught times the sine of theta to get viy. In case you're not sure where that comes from, remember that what sine means, sine of an angle is equal to opposite over hypotenuse. So what I'm saying then is sine of theta is equal to opposite, which is viy, divided by hypotenuse, which is v naught. So then to solve for viy, I'm going to multiply both sides by the hypotenuse. And then times hypotenuse on this side. And so then, since the hypotenuse is just v naught right here, I'm saying sine of theta times the hypotenuse is equal to viy. So that's where that piece is coming from. Now for vx, am I going to use sine, cosine, or tangent for that part? Well, since this vx is adjacent to the angle, we're going to be using cosine, because cosine is adjacent over hypotenuse. So that means that the cosine of theta equals adjacent, vx, divided by hypotenuse, v naught. So multiply both sides times hypotenuse, and vx will be equal to v naught times cosine, of theta. Okay, now I've got my resultant vector, v naught, the hypotenuse that I started out with, rationalized into x and y components using sine and cosine. The other thing that I want you to notice when we're talking about type 2 projectiles specifically is that the angle that we start out with over here is the same size as this angle that we end with. So what we see is a vector, a velocity vector that's going up, and it's getting smaller and smaller and smaller. As we're going up, my x velocity stays constant the whole time because there's no force causing it to speed up or slow down. So everywhere we go, that velocity is always the same size. And it's the same size when we get back down here. However, my y velocity is changing. So we start out, it's this big piece right here. But as we go up, this velocity is getting smaller because it's slowing down. Smaller still. And then at the apex, that vertical velocity is 0. So velocity of the y apex is equal to 0 meters per second. And then as it's going down, that vertical velocity starts to increase, but it increases in the negative direction. Until we get all the way back down here, and it's back to the same size that it started with in the beginning. So something that's really important to notice is that this final velocity, v final y, is equal to negative v initial y. So whatever you get at the beginning, v naught times sine of theta, for that initial velocity in the y direction, that's going to be equal and opposite to the velocity that you get at the end, your final vertical velocity. So here, that velocity was positive. Here, that velocity is the same size, but it's negative. And theta is the same here and here. That's why this is the same size. We're slowing down for the same amount of time that we're speeding back up. So we get back to the same speed, but in the opposite direction, down now. However, my x velocity stays the same the whole time. Up here at the apex, we only have a horizontal velocity. And then down here, the horizontal velocity is still the same, so that means when we find the resultant between our x and y vectors, this size vector here will be equal to this size vector, but instead of pointing up into the first quadrant, it's actually pointing down into the fourth quadrant. So it's got a positive x but a negative y. Here, positive x and positive y. Positive x, negative y. We also know, of course, that the time up is equal to the time down, which means that the total time can be described as time up plus time down, or it can be described as 2 times the time up or 2 times the time down. Either of those will be very helpful. And finally, we need to remember that this height and this height are the same. So what does that mean? The total change in vertical position is, total change in y is, from the very beginning to the very end. It's 0 meters. Here, this apex, that's the maximum height. And at that point, we're going to be at 0 meters per second. But down here, we're not at 0 meters per second. We're at the opposite velocity, opposite vertical velocity of whatever we had here. and it's in the negative direction. So those are some basic notes for you over type 2 projectiles.